And welcome to another video from HEGARTYMATHS. It's a Core 4 Maths A-level video, and we're doing a topic within integration, and we're finding out volumes of revolution. As always, for more help with your math studies, do see YouTube, Twitter or Google+. So, we're dealing with chapter 6, the volume of revolution, in the Edexcel Core 4 syllabus, but it should be applicable to most other core maths modules. Just taking a look specifically what we need. We need to be able to evaluate the volume of revolution. The formula pi y squared dx is required, but it says but not pi x squared dy. Okay, so we can ignore that, not worry about that. But it says students should be able to find the volume of revolution given parametric equations. So we're going to cover both of these in this video. To start with, as always, let's just talk about the big picture and what we're trying to do and why the formulas work. The volume of revolution, what is this? Well, I've drawn two pictures on autograph to show you. Imagine you worked out an area under a curve. Imagine you worked out this area under a curve, let's say here. Okay, that area. And you swept that area 360 degrees. Or we might say 2 pi radians all around the x-axis, okay? Then you would get this volume of revolution, you would get volume. And if you looked at it in the side, it would look like this sort of a shape here, and what we're trying to work out is the volume of that shape, and it's called the volume of revolution. Okay, that's what we're trying to do. So it's when the area is swept around 360 degrees, you can see the sweep 360 degrees, or even you might call it 2 pi radians or 360 degrees. What is the volume when you sweep that area all the way around the x-axis? So that's what we're trying to do. So in order to get us to that point, what we're going to do is we're going to use a bit of autograph software here in order to explain where the formulas come from. So let's go to autograph. Here we are in autograph, and what I've done, here we have the x-axis, here we have the y-axis, and I've drawn for us a curve. The curve is as follows. So what I would like us to do is I'm going to put a point on the curve. So I'm going to highlight my curve, and I'm going to put a point on the curve, and I'm going to put the point when x is 1, and I'm going to highlight the curve again, and I'm going to put a point in the curve when x is 1 plus h for some number h. The computer always takes a constant to be 1 at start, so this is going to end up being where x is equal to 2. In order to just move it along, I'm going to move it up to about here. Okay, so they're my 2 points on the curve, and what I'm going to do is I'm going to highlight those 2 points, and I'm going to find the area between them. Now I'm going to use the trapezium rule, it doesn't matter what rule, and I'm going to divide it up, let's say 20 times, so it's nice and accurate. And there is my area under the curve, or an approximation for the area under the curve. Okay, so I'm at this point now, I've got the area under the curve. Now what I'm going to do is I'm going to highlight that area, and I'm actually going to tell the computer to sweep it round 2 pi or 360 degrees about the x-axis. So I'm going to go find volume. And I'm going to rotate it around y equals 0, or the x-axis, and the computer starts doing that. You can see the computer sweeping this volume out for us here, and it makes that shape as we saw in the previous. So there we go, that is the volume I'm trying to find. Okay, so I'm going to try and find that volume here. Now what I'm going to do here is I'm going to show you where the formula, which I'm going to tell you how to use later, actually comes from. Suppose I highlight that point there, and suppose I make h go in steps of 0.1, and let's say I make h go down. H is currently 2, so this point is x is 3. What if I make h go down and down and down and down to there? Now can you see, when h is very, very small, when this h is very small, actually what we've got is it looks like a circle, but it's got a bit of thickness in it. It's actually a cylinder. Well, closest to a cylinder as you can get. You can imagine where h is very small indeed. This thing here being a cylinder. Okay? So as h gets smaller and smaller, this volume here is a cylinder. So, as we're working out the area, it's actually the sum of loads of little cylinders. As this h number gets very small, you can see me now increasing h. To work out that volume, what we're actually doing is we're working out the volume of loads of cylinders added together. And at this point here, I'm getting up to h is 2, where I was before, and that's the volume. Okay, so going back down to when h is very small here, I'm going to make it back down. What I'm doing to work out that volume, what I'm going to do is I'm going to add up the volume of loads and loads and loads of cylinders. So I'm going to make h tiny here again, just to make it clear that we've got cylinders. So there we go, that's pretty small there. Now, how do you work out the volume of a cylinder? Well, the volume of a cylinder is the area of the face, which is going to be pi r squared. What's r? R is the radius, but in this case, it's actually the height of the curve. So it's going to be pi y squared. And we're going to times it by this little movement in x, which is dx, a tiny little movement in x, which we're going to call dx. So I'm going to go back now to my volumes of revolution slide, and here is the formula. I'm just going to explain the components of it. If I'm working out the volume, okay, I am working out the volume of each cylinder, which is pi y squared, okay, multiplied by dx. dx is the tiny little movement in the x direction. I'm summing all of those volumes up. So there's the integral does the sum for me from x is equal to a, okay, all the way up from x is equal to b, and I'm summing those cylinders up. And hence, that is some of the rationale behind why this formula works here. If I want to work out the volume of an area under the curve y equals f of x when it's swept 2 pi radians around the x-axis, what I do is I square the function, I integrate that between x is a and x is b, and I multiply it by pi, and that's how I do it. So let's have a go at one of these type of questions here. Example 1. The region R is bounded by the curve y equals sine 2x and the x-axis, and the lines x is equal to 0 and x is equal to pi by 2. Find the area. Okay, firstly I'm just going to draw a quick sketch. You don't need to do this. Okay, but normally sine x looks like that, but this point here is pi and this point here is 2 pi. But sine 2x, okay, actually doubling the x here actually halves, actually squashes everything by a factor of 2. So actually in this case it would go up like that to pi by 2. Okay, so that's what the sine 2x graph would look like between 0 and pi by 2. So this is y equals sine 2x. And what we want to work out is we want to work out this area here, r. So what we're going to do, r is equal to the integral between 0 and pi by 2 of sine 2x dx. Okay, now sine 2x, that's one of the functions we can integrate. Because we know that if y equals sine 2x, dy by dx equals 2 cos 2x, and because we know if the original function was cos 2x, that dy by dx is minus 2 sine 2x, we know the integral of sine 2x is equal to minus a half cos 2x. And we're going to put in 0 and pi by 2, and when we do that, when we put in pi by 2, we get cos of pi, and cos of pi is equal to minus 1, so we're going to have minus a half, get minus 1, subtract what we get when we put in 0, and when we put in 0, we get 1. So minus a half, this would be minus 1 minus another one, which is minus 2, times minus a half, which would give me the answer of 1. Okay, so the area R is equal to 1. Okay, so we're done in that regard to start with. Okay. Okay, the next part, what we're going to do now is, we want to find the volume when the solid is rotating 2 pi around the x-axis. So we want to rotate this region R 2 pi all the way around the x-axis here. So we know the formula for the volume. The volume is equal to pi, the integral between 0 and pi by 2 of y squared dx, which is going to be pi, the integral between 0 and pi by 2, y squared is going to be sine squared 2x dx. So that's the integral we want to work out. Now we don't know the integral of sine squared 2x, but we can remember our double angle formulas. Remember the double angle formulas that tell us the following. It tells us that cos of 2x is 1 minus sine squared of single x. So therefore cos of 4x is equal to 1 minus sine squared 2x. Okay, so making sine squared 2x the subject, it'd be 1 minus 2 sine squared, 1 minus 2 sine squared 2x, sorry about that. So therefore 2 sine squared 2x is going to be 1 minus cos 4x, and therefore sine squared 2x is equal to a half minus a half cos 4x. Okay, so instead of trying to integrate sine squared 2x, which I can't, I can integrate this. So in place of sine squared 2x, I'm going to put the following. So what I'm going to do is I'm going to integrate between pi times the integral between 0 and pi by 2, a half minus a half cos 4x dx. Okay, so let's keep going with this. So what I'm going to do then is I'm going to actually integrate this. So keep the pi there, integrate, put square brackets, integrate a half, you get a half x, and integrate minus half cos 4x. What you get when you do that, you're going to get yourself minus an eighth sine 4x between 0 and pi by 2. The reason that is if you differentiate minus an eighth sine 4x, you would get a half cos 4x. And now you slot in pi by 2, so keep that pi there. Slot in pi by 2 and you get pi by 4, subtract an eighth sine of pi. Sine of pi is actually, so you get a minus an eighth sine of 2 pi, which is 0. And you slot in 0, get 0 minus 0. So what you get there, you get pi multiplied by pi by 4 minus an eighth sine of 0 by the, this is going to be 0 again, just to make that clear. So you're going to get yourself pi squared over 4 for that volume. And you're done. That's the volume there, and you're finished this question. Okay, so that's the volume when you rotate this region R 2 pi or 360 degrees around the x-axis. Okay, and every example is very similar to that. The one other thing that the examiner said we need to know, we need to be able to integrate and find the volume of revolution when the curve is given parametrically. So, imagine you've got the curve, and instead of it given in the form y equals some function of x is given in terms of a parameter t, y is given in terms of a parameter t. When x is a, you've got this t being some number t1, and when x is b, t is some other number t2. The volume of revolution, it links in, it's similar to the area. If you remember, the area of a normal curve is the integral between a and b of y dx, and when we work that out parametrically, the area is the integral between t1 and t2 y x by dt times dt. So we're doing a similar thing here. If the curve is given parametrically, we still have our pi, which is as we wanted. We still have our y squared, and instead the rest, these numbers are between t's, and we have dx by dt multiplied by dt here. You can think of it as the dt sort of cancelled to give you the dx you wanted, but it's very similar to the area given parametrically. So that's the formula we need to use and you need to be aware of. So let's have a go at a question. Example 2. The curve has parametric equations x is t, 1 plus t, y is 1 over 1 plus t, where t is bigger than or equal to 0. The region is bounded by c and the x-axis, and the lines x is 0 and x is 2. Find the area. So firstly, the area of R is going to be the integral. In general, is the integral between x is equal to 0 and x is equal to 2 of y dx. Now, the curve is given parametrically, so we're going to have to find this in terms of t's. So the first thing to say is when x is 0, then we're going to have to find t, then t, 1 plus t is equal to 0. So t is either 0 or t is minus 1. And we're going to ignore this one because we're told that t is bigger than or equal to 1. So we're going to ignore that. Okay, next, when x is equal to 2, what's t going to be? Well, we're going to have t, 1 plus t is equal to 0. And we expand that out, that's going to be t plus t squared is equal to, is equal to 2. My fault, it's equal to 2 there. And we can subtract 2 off both sides and we get t squared plus t minus 2 is 0. Factorising that, it would be t plus 2, t minus 1 is 0. And actually solving that, you would get yourself that t would be minus 2 or t would be 1. And you're going to ignore this one because it can't be negative. So, the last thing we're going to do, we want a dx by dt here. So we know that x is equal to t plus t squared, so dx dt is going to be 1 plus 2t. Okay, so let's have a go at writing this. This is therefore the integral. When x is 0, t is 0, so it's going to be from t is 0. When x is 2, when x was equal to 2, t was equal to 1, so it's between t is 1. Y, well we know y in terms of t is 1 over 1 plus t, so it's 1 over 1 plus t. And we have dx by dt, which is 1 plus 2t, and we're going to multiply it by dt. Okay, so this is therefore the integral between 0 and 1, 1 plus 2t over 1 plus t dt. Okay, so this is the integral we want to work out. It's a quotient, that means it's a division. If it's a division, there are two options they can usually be. The first is it a logarithm integral? Is the top the exact differential of the bottom? Well, no, it isn't in this case. So usually partial fractions is the best way to go. So I'm going to do a bit of side working. And we want to write 1 plus 2t over 1 plus t as partial fractions. Now, the top has power 1, t is 1, the bottom has power t is 1. So when you divide the same powers, you get a constant plus b, another constant over the linear factor on the bottom, or the factor on the bottom. So therefore, multiplying up, my next line will be 1 plus 2t is equal to a, 1 plus t plus b. Okay, in this case, I would let t be minus 1. If t is minus 1, I'd get minus 1 here is equal to b. And then what I could do is I could let t equal 0, let's say, and I'd get 1 is equal to a plus b. And b is minus 1, so therefore a must be equal to 2. Okay, so therefore my integral above, my integral between 0 and 1 of 1 plus 2t over 1 plus t dt, I could write that as the integral between 0 and 1 of 2 over 1, of a, which is 2, plus b, which would be minus 1 in fact, So it would be minus 1 over 1 plus t dt. I could integrate this. The integral of 2 would be 2t. So integrating this would be 2t minus, is the top the differential at the bottom? Yes, it is. So minus log of 1 plus t between 0 and 1. And subbing in 1, I would get 2 minus ln 2. And subbing in 0, I would get subtract 0 minus ln 1, which is 0. So my answer would therefore be equal to 2 subtract ln 2, and that's my answer for the area in part A. So it's 2 subtract ln 2. Okay, so going up back here, the area for A was actually R is equal to 2 subtract ln 2. Okay, done. Now, the next part, I want to find the volume of revolution when R is rotated about the x-axis. So for part B, I'm going to use the formula. The volume is equal to pi, the integral between t1 and t2, y dx by dt dt. That's the formula I'm going to use for this one, and it's y squared dx by dt dt. Now, this is going to be equal to pi. The integral is, we've worked out the t1 and the t2 before, it's the integral between 0 and 1. 0 and 1. We've worked out dx by dt before. Dx by dt was 1 plus 2t, and y squared is going to be equal to 1 over 1 plus t squared. So I'm going to get 1 over 1 plus t, that squared, and I'm going to get 1 plus 2t dt, 1 plus 2t dt. So this is the integral I'm going for here. So it's pi, the integral between 0 and 1. This would be 1 over 1 plus t squared. So I get 1 plus 2t over 1 plus t squared, t all squared. Okay, dt. Now, is the top the exact differential of the bottom? Well, it isn't, no. So again, I'm going to use partial fractions. So what I'm going to say, the top is power 1, the bottom is power 2. So 1 plus 2t over 1 plus t squared. As partial fractions, you would get a over 1 plus t, and you would get b over 1 plus t squared. There's no constant term, as the power of the top is lower than the power of the bottom. So multiplying up, 1 plus 2t would be equal to a, 1 plus t plus b. You would let t equal negative 1 again, and you get negative 1 is equal to b, and you would let t equal 0 again, and you would get 1 is equal to a plus b, and you would get a is equal to here 2 again. So therefore, this would be integral between 0 and 1 of a over 1 plus t, which is 2 over 1 plus t, and it would be minus 1 over 1 plus t squared dt. And now we can integrate. Well, here is the top differential of the bottom. Well, nearly. It would be 2 ln 1 plus t. And this here, well, this is actually 1 plus t to the power of minus 2. So this is a simple polynomial. Add 1 to the power and divide. So it would be minus 1 plus t, add 1 to the power, would be minus 1 over minus 1, between 0 and 1, which is pi 2 ln 1 plus t plus 1 over 1 plus t. Put 1 in, you get pi, and it would be 2 ln 2 plus a half, and put 0 in, subtract 2 ln 1 plus 1, and it would be pi 2 ln 2, a half minus 1 would be minus a half. And that now is my answer for the volume, and I have done this question. So just to go back up to the top and think what we did, when we're working out the area under a curve given parametrically, we use the area is equal to the integral between t1 and t2 y dx dt multiplied by dt. Okay, and we had to use partial fractions in this case, and when we use the volume, we use that formula there, and we're done. So to finish with then, make sure you read chapter 6, page 111 to 114, and do exercise 6i, questions 1 to 4. Thanks for watching.